Good morning, good afternoon, everyone. Thank you for joining us. We are excited to present this webinar, From Chaos to Clarity, Solving AI Data Pipeline Challenges with the VAST Data InsightEngine with NVIDIA. I would love to introduce our speaker today. This is Aaron Chasen. He's Vice President of Product and Solutions Marketing here at VAST Data. He's going to run through this with us. And then I also want to share with you all, if you have questions today, we encourage you to ask them. You can do so by clicking the Q&A tab on the right-hand side panel of your screen. Click in your answer there. Or click in your question there, excuse me. You can also hide your name and ask anonymously if you would rather. We're going to save questions for the end, most likely. If we do not get to your questions today, we are going to follow up with you. So we will try and get you those answers as fast as possible. Without further ado, I will introduce Aaron.
Here we go. Thanks, Annalie. I appreciate it. So today we're going to be talking learning a little bit about AI data pipelines and some of the challenges that a lot of our customers are seeing in trying to roll out AI, whether that's in a training environment or whether that's focusing really more on what a lot of the shifts are happening today, which is moving more towards inferencing, especially in enterprise accounts. And I'll be talking about the VAST Data InsightEngine with NVIDIA, which we pre-announced a couple of months ago. We've been working closely with NVIDIA on developing this release, and we'll be highlighting it and showcasing it at GTC in a month. But we want to start sharing with everybody kind of the solutions this is and the pain points this is solving. And so with that, we'll go ahead and get started. So first of all, we'll go ahead and share this out. And we'll get started. All right. So as I jump into it, the first thing I want to do is lay out sort of a basic understanding of the AI pipeline fundamentals. Obviously everybody that's going to be on this call is going to have a different level set of understanding and experience, and so I want to make sure we've all got a similar terminology and vocabulary. Then we're going to dive into the VAST Data Platform. So what is it that we've done and how have we innovated around our architecture to be able to really simplify infrastructure in the data platform for being able to accelerate these pipelines. And then we're going to dive directly into the enterprise AI moment. So what's happening in the market today? What are the challenges that a lot of enterprises or accounts are dealing with in trying to kind of unlock your particular set of data sets and be able to leverage large language models against your data to be able to deliver specific insights for what you're trying to accomplish. And then I'll go through the InsightEngine itself and kind of what we've innovated around in partnership with NVIDIA and in order to be able to help you accelerate this adoption. So starting with the pipelines. I think a lot of people are familiar with this, but I want to level set on kind of how does data flow through the AI pipeline from data capture all the way through the actual the actual inferencing against the data. So it starts really with data ingest. So when building AI models, the first thing that it's really need to do is capture what is all of the data that we want to be training against these models. And data ingest typically requires unstructured data stores and some structured. So as you pull in this data from a variety of different data sources, it could be scraping the internet, it could be pulling from different file shares or object stores. These things need to be dumped down into a repository in which we can start gaining insight from them. So it starts by dropping these into typically file or object stores, and then we move that through the pipeline to data preparation. So the second phase of this is going to be taking that massive set of data and starting to manipulate and prepare that data for the actual data sets on which we want to do the training. So if you're doing some of these large foundational data models, it's oftentimes pulling out a lot of unnecessary data that we don't want to do that training against. That's going to be cleansing that data, preparing that data, and oftentimes then storing that into more structured environments that then allow us to create tokens that we're going to use to do the training against. The next stage is going to be moving the data set on which we want to do the training into a data training platform that we're then going to be pointing these, hundreds to thousands to tens of thousands, and nowadays in the largest data centers, hundreds of thousands of GPUs against this training set in order to be able to then train these large language models that we're going to be using to be able to do the inferencing down the road. Now, once those models are created, the next step is to put those models into a model catalog. So the model catalog, think of this as being something like, the NVIDIA NIM catalog. This could be Hugging Face. These could be the catalogs for different large language models that you're going to be pulling from. Those are typically going to be stored in some sort of either a file or an object store. Once those models are being created, and some of these examples might be, if you're using ChatGPT, this might be GPT 4.0, 01, 03. That model catalog, I'm going to then pick from that which model I want to use to do my inferencing against. And that's the next phase of this, which is that inferencing phase, where I now want to query against that model to be able to get responses and insights. So I would basically pull a model out of the catalog. For any of you who are familiar with, ChatGPT again, you can go into your client, you pick which model you want to be querying against. That model gets leveraged. I generate my query or my prompt, my question that I want to ask. That gets then give a response, and that response and the entire knowledge chain of that entire pipeline needs to be logged. All right, and this is for really compliance and regulatory purposes. Increasingly, there's compliance and regulatory requirements out there that say I need to be able to attest to not only what question did I ask, what model did I use, what data set was that model trained on, what was the response that I got. And so if there's any discovery requirement or to be compliance purposes, I can have a full chain of knowledge of what was it trained on, what model was I using, again, what prompt did I do, what response did I get, and I need to log that for any legal or compliance discovery down the road. The other reason for being able to log these responses is there's the feedback loop back into the model training environment, which allows me to then tune and improve the quality of the results over time. And so this is the basic AI pipeline, from ingesting all of the data, tuning that down into just the data that I want to train against, training against that data, and then inferencing against that, and then logging and tuning back through. That's the basic pipeline. Now, that first phase, from data ingest all the way through to the cataloging, that's going to be the model training phase. And then the inferencing phase, like I went through, is the extracting of which model you want to use, doing your query against that, and then logging that for long-term compliance and regulatory purposes. Now, most of the focus today has really been on the middle. And if you look at this entire pipeline, what we've been trying to solve for is the challenges of the fact that most of today's traditional approaches don't really meet the needs of the entire pipeline. There are point products that can be able to solve different points of this, but nothing really out there today until VAST has been able to support the entire knowledge chain here and the entire data pipeline. And most of the buzz for the last, probably 3, 4, 5 years has been around this training phase. So when you think about sort of the buzz since 3.5 was announced back in November 30th, 2022, has been, how do we build bigger and better and more technically accurate language models? And you see the open AIs, the AI XAIs, the Geminis of the world are all competing to kind of create the biggest and best model out there. That's really been what a lot of the press and a lot of the focus has been on the last couple of years, is how do we feed massive amounts of data to tens to hundreds of thousand GPU farms to be able to build the best possible model. But long term, where the real focus is going to be on is kind of these outside pieces. How do I capture the right sets of data and curate that, whether I'm building models or whether I'm gathering my enterprise information to feed that into an AI pipeline for enterprise? And then on the right side of this is, how do I deploy that model? How do I push that to even edge devices and client devices where I may want to do inferencing in particular environments? Those outside pieces is increasingly especially where enterprise customers are trying to look at to find out, how do I integrate the entire value chain for my business, not just creating the models, but leveraging those. Now, if you look at the first half of this, typically what's going to be storing that data ingest and data prep phase is going to be your traditional cloud and legacy storage environments. These are going to be your data lakes and data warehouses that are capturing all of your structured and unstructured data and allowing you to be able to prepare that data over time in order to be able to prepare it to be moving it into the training phase. The training phase has historically been focused by the parallel systems of the world that are able to create, very high bandwidth and throughput of reads and writes to those GPUs in order to keep those GPUs fed 24/7, 365 to really accelerate the time to model and being able to produce these large language models as quickly as possible so that they can continue to out-innovate their peers. The third phase then is then moving the resulting models into environments where I can then distribute those. And this typically then goes back to, again, that cloud and core edge systems world. So whether I'm doing my inferencing in the cloud, in a client, and if I'm going to, GPT or Grok or whoever to be able to do it there, or if I want to be able to push these out to edge devices. So you increasingly are seeing, pushing it into a manufacturing facility, pushing different models out into client devices. So these are not only going to be your traditional sort of AI infrastructure environments, but these also could be pushed out to gateway devices and other smaller form factors that are able to do the inferencing operations at edge locations. So all of these are different places where I can store and capture my data, train against that data, and then act against that data. And each of these types of environments typically require different sets of technologies from a variety of different hardware and software vendors. Each of those takes time, it costs money, and you're able to invest and manage these. And then also another big challenge, especially when it comes to time to value, is the time it takes to move data between these different areas as well. Because oftentimes in many environments, the sort of ingest and preparation area is one set of infrastructure. The resulting tokens that I want to train against need to get moved or copied into a training environment, which takes time. And then the resulting models need to get moved or copied into a distribution environment where I can then go and leverage those for my inferencing operations. And obviously, time is money in these environments. So being able to reduce the amount of time required to either move, or in many cases, what we're trying to do is eliminate the requirement to move by having a single platform that stretches across this, really dramatically accelerates these processes. Now, the final challenge, of course, is also operational complexity. Being able to integrate all these systems, deploy them, integrate them, manage them, upgrade them, operate them, and deal with the multi-vendor approaches that are required to be able to make this entire system work becomes a significant operational challenge, which comes with its own set of costs. So these are kind of the sort of existence today, leveraging technologies that might have been created before. So what is it that we're really doing? So I want to talk a little bit about what is unique and what VAST has been doing to innovate to really architect a brand new infrastructure, a brand new architectural approach to deploying a data platform and data services on top of that platform that supports this entire chain, this entire data pipeline. So what we've really done is we've taken learning from the past. If you look back to when this whole push towards GPU-based AI acceleration really started about 10, 15 years ago, the technologies that were built and existed at the time were really designed for a problem of the past. They were really designed for a problem of cloud scale, many different users trying to get to lots and lots of data. Or you also had the world of HPC, where you needed to get lots of clients to a single data set in order to be able to do operations. Now, from a cloud perspective, and where most of these technologies, whether it's storage systems or whether it's data warehouses built on top of those systems, whether that's on-prem or in the cloud, they're all built on architectures that really fundamentally found their roots in that sort of Google white paper back in the early 2000s that talked about being able to distribute data across many numbers of nodes to allow large data sets to scale horizontally while still being able to serve the needs of many, many requesters coming into that data set. But it has its own limitations that I'm going to talk a little bit about. And we really architected a brand new approach, and that's what I want to go through. So what were the challenges? The approach that's taken by most of the traditional vendors today of being able to build scale out systems by effectively breaking a a data set down into logical chunks and then distributing those chunks across many numbers of nodes, solved this specific problem of 20 years ago. And the way I used to like to leverage this is the idea of a phone book. If you go back to the 90s, where you were looking at very large scale-up systems for transactional workloads, every single that storage platform had a dual controller system typically that had the entire phone book. And so if a request came in, it had the metadata that knew where all of the different phone numbers were. But once that phone book got very, very big, the amount of time it took to search all that data was increasingly challenging, and you started getting longer latencies. It also became difficult to scale out because you could only, or scale up because you only had so much capacity you could fit underneath these systems. And so that Google approach, which everybody started adopting, was sort of taking that phone book and splitting it into the different parts of the alphabet. So I'm going to give multiple nodes a portion of that book. Node 1 on the left might have all the A's and then all the B's, and then another node has all the C's and another had all the D's. So now when a client comes in and makes a request for, John Jones, I may be connecting to a host that has the B's, and so it says I don't have John Jones, but it can look horizontally across to another node that has all the J's, looks it up, and services that response. The advantage of this splitting up that entire data set across many different nodes allows you to be able to scale to very large capacities while still being able to keep serviceable response times by splitting up the responses across n number of hosts. Now, the good news is these systems could now get very, very large, could service the requests of many different people looking for a variety of names across that phone book. The downside of this, however, was as the node count increases, the amount of crosstalk across these systems in order to do these lookups across the hosts starts to dominate the amount of I/O traffic within the system. The more nodes there are, the more lookups need to happen, and the more of the network and the resources are being spent on those lookups across those nodes. So as an example, if I've got 2 hosts, there's 1 connection. If I've got 3 hosts, there's 3 connections. Not bad to manage. Once you get to 40 hosts, it's about 780 connections that you now have to manage these lookups across. And that's why most of these systems typically only scale to 30, 40 or so nodes before the traffic between those starts to become that performance bottleneck, limiting both scale and performance of these boxes. And of course, as the node counts increase, the performance decreases as that increases over time. And these are the things that we're trying to overcome. Performance challenges at scale. And another key thing is that every single node within these clusters needs to have a very similar hardware configuration in order to be able to perform consistent performance across that entire data set. So they have very rigid personalities and strict rules and requirements on how these systems can be assembled and upgraded. So what have we done? What we really did was reinvented how you architect a data platform system to be able to store these types of data at very, very large scales that we're seeing today, all the way into the exabyte range, which is what we're seeing, not just the big cloud players, but even enterprises now. We're getting into the hundreds of petabytes and larger. So what did we do? First of all, we leveraged a brand new technology back in 2016 when we started, leveraging the NVMe fabric over fabrics. What this allowed us to do was really rethink from the ground up how we want to be able to architect the data services leveraging this new fabric technology. So what is it that this allowed us to do? First of all, by leveraging NVMe over fabrics, this allowed us to completely disaggregate the stateless compute from the physical persistence layer where the solid state disks reside within the platform. What does that mean? That means that hosts that are coming in to the compute nodes at the top, the compute nodes themselves have no persistence, have no state, have no, like I said, state across those nodes. All of the state, all of the persistence, all of the data sits on the shared metadata and SSD nodes on the D node side of this configuration. What this allowed us to do is then have every single compute node can now, through NVMe over fabrics, mount to every single SSD. as if they're local to that compute node. And so we can actually scale now to n number of nodes. It can be almost infinite scale, but deliver the performance at 99% the speed of a local SSD to that client. The second thing that this allows us to do is now, because of that performance, because we're getting basically native SSD performance to the C nodes, it allows us to push two core things down into the persistence layer. One, metadata. So all of our metadata does not exist in the compute nodes. That metadata sits now down into that persistent SSD layer. And the second thing is it allows us to put our write buffers down into persistent storage as well. These are two very, very important fundamental changes to how we architected based on leveraging this NVMe over Fabric technology. By pushing metadata and write buffers down, that eliminates the need for dual controller systems or single controller systems. We know are no longer limited to that sort of 40 node upper limit where you start to have crosstalk that creates problems, because that crosstalk is really memory lookups and writes. It allows us to push all that down into the persistence layer, so we can now scale those stateless C nodes to hundreds, if not thousands of nodes, and being able to get that 99% of SSD performance to every one of those devices. The next thing allows us to do, as we created this new set of metadata, was we from scratch built a metadata area that allowed us to assume that we were going to be able to support any protocol. So we support file, we support object, we will be supporting block imminently. You'll hear more about that this week. And also tables on as native elements of equal value on our element store that sits on persistent disk. So there's no protocol translations. If I am a built as file and I want to now access it as object, I don't have to have any gateways. Every single protocol, file, object, block, table are native elements on the element store, and all of them get full performance to exabyte scale. The final thing is because we can scale to these massive environments and deliver parallel performance to all of our C nodes and all of the client devices, we need to make sure that this is the most highly available and highly resilient platform out there, so that companies feel confident that they can support all of their data on a single platform in this single cluster. So we reinvented how we did erasure coding. We do 146 plus 4 erasure coding, which means that we get only 2.7% overhead, making very, very highly efficient use of our SSDs while being able to have extremely high resiliency. We also reinvented a new way of doing data reduction. So rather than just traditional compression and deduplication, we actually invented a new methodology that we call similarity. Very similar to vector approaches to doing vector embeddings in the AI world. It effectively allows us to look at the entire data set that's stored inside of this entire exascale environment, find all of the blocks that are similar to each other, and only store the differences between those. So it's a new approach that allows us to be much more efficient. The combination of the erasure coding plus our similarity allows us to be anywhere between 2 to 2.5 times the data reduction of any of our peers. Again, making a very low cost approach of our SSDs. We actually can deploy these environments, giving you the performance of SSDs, but really at the cost of spinning disk. And from a resiliency and availability perspective, we've able to achieve upwards of 6 nines of availability, and more impressively, 14 nines of durability, which is 1,000 times more durable than what even Amazon provides for their object stores, for their storage offerings. So you can really trust that not only are you going to be available 24/7, 365, but it's literally thousands of years between data loss, and you can trust the data on these platforms. Now, on top of this architecture, we've created our data services, and they fall into kind of 4 categories. The first one at the top left is the data store itself. So the data store, we believe, is the world's best storage platform. Again, it allows us multi-protocol access to file, to object, to block, storage devices, and it allows you to get literally terabytes of throughput at milliseconds latencies at any scale across all protocols simultaneously, with no degradation as you move from one protocol to the other. And in fact, you can save things as files and access them as objects, and vice versa, because all it is a protocol shift on a common element sitting on the back-end element store. The second thing is the database. So the database is a set of data services we announced a little over a year ago, which is our transactional data warehouse. It's a tabular structure that runs as an equal element on our element store. It allows us to be able to ingest writes in rows and then save them as columns on the persistent backend. It allows us to be able to automatically and stream data directly into tables so that we can actually so you can analyze that data in real time as it's flowing into the system, both the real time data that's flowing in transactional nature, but also be able to correlate that with petabytes to exabytes of data on the back end, allowing you to sort of bridge that gap between the transactional world and the analytics world in a single system, giving you real time access to your data. We'll talk more about how that applies to AI and to our insight engine as we go forward, because a thing I haven't mentioned yet is we're also adding vectors to this store. So not only can we do transactional rows, analytical columns, but we'll also be able to store vectors directly in this data store for vector analysis in AI RAG operations. And the final piece on the right is the data engine. So the data engine is a parallel containerized computing environment. It allows us to be able to have our own container runtime, not only for running our CNode software, but also to be able to run third-party functions and microservices natively on our arrays, and have an event-based trigger system to actually trigger operations against data as it flows through that pipeline. And I'll talk more about that in depth in a couple of minutes. The final piece is the data space. Data space effectively allows you to access data across multiple clusters anywhere they may reside. So you could have clusters on-prem in a colo facility. You can even have VAST clusters in cloud providers like AWS or GCP. And data can be saved in one and accessed in real time at another location without having to replicate that data to secondary sources. So the data space allows you to be able to centrally access data across any cluster that you deploy, on-prem or off-prem, allowing you to, again, more easily move data through that pipeline and to be able to access for example, in inferencing operations, regardless of where those the catalogs may reside. So the goal here with this system is to take this challenge that we had of a very complex environment and have a single system that can provide the exascale file and object requirements to ingest all of your data, the analytics and the database environment in order to be able to cleanse or prepare that data for whether that's training or inferencing, the ability to have parallel performance to every single file and object in your system, again, terabytes of throughput at millisecond latencies across any protocol, so you can feed those GPUs for training operations, and also to be able to ingest from those GPUs during checkpoint operations in Windows. And then finally having the global namespace or that data space to be able to make those resulting models available to any geographic location where you want to be doing your inferencing. A single system that supports that entire pipeline, again, from ingest to training to inferencing, and then be, again, logging all of that for compliance and regulatory purposes. It really allows you to have one system to buy to support that chain, one system to manage, and there's no need to physically move data between those locations. I don't have a sort of data prep space, move data into a training space, move data into an inferencing space. One platform allows you to do all of that. So as soon as the data is ingested and prepped, I can immediately start training against that data set in place with all the parallel performance that I require. And then with the resulting catalog, be able to access that from any location in order to do my inferencing at my core or in my edge environments. And together, of course, what that means is lower CapEx, less to buy, lower OpEx, much simpler to manage at scale, and a faster time to value by not having to move and copy data through that pipeline, be able to have a single platform to access for whatever phase you happen to be in. The result of this is that we've been obviously very successful over the last couple of years. We've got hundreds of the largest enterprises and model builders who are now leveraging VAST technology to be able to support traditional enterprise workloads, data warehouse workloads, backup and recovery environments, all sort of day-to-day operations for businesses. but then also to be able to take that data and move it through the pipeline for AI operations. And today, we are proudly the foundation for some of the world's largest AI foundational models like Inflection and XAI and Genmo and ServiceNow and many of the other sort of brand named foundational models that we aren't at liberty to share. But then also some of the very largest enterprise accounts that are on the bleeding edge that are trying to sort of innovate and get out in front of this wave. The Miters, the Samsungs, the Volvos, the Sonys, you name it, across almost every industry that are looking to leverage their data against the models that oftentimes that are provided by the model builders, or even tuning and creating their own to be able to drive value within their industries. And so we're really proud to be that foundation for literally hundreds of the largest enterprises and largest model builders out there. So I now want to shift a bit away from sort of, there's a bit of a focus on the model training there into the enterprise world. And we really do think that AI over the last year has started really accelerating into this AI moment. Whereas the last couple of years have been focused more on the model training and those foundational models, a couple of things that have really happened that have shifted that focus to enterprise. One, the emergence of RAG last year was kind of, everybody, the buzz was of retrieval augmented generation, and how do I unlock the value of my enterprise data corpus or my data set without having to give my data to a model builder or give my data into a model set through tuning. I want to be able to unlock all of that data for inferencing to be able to do things like chatbots or real-time, customer experience environments, or being able to do video editing or video manipulation in real time. Lots of different use cases that are starting to emerge, and RAG was the big hot topic last year. As the year went through, agentic AI started becoming more of the buzz, and not just a human being on a keyboard typing a prompt into, prompt engineering into a GPT window, but programs, agents that are able to actually query and iterate against those queries and work in combination with other agents in order to automate a process leveraging AI. So we've got companies, for example, doing software development where they have agents that want to do this, create software, and another set of agents that are doing QA against that software, and maybe another set of agents that are tracking the flow through that development pipeline that are more like a PM type function. So RAG and agentic AI have been kind of really starting to shift this conversation towards how do enterprises start leveraging this and really generating value out of the advances that these large language models have provided. And more recently, I won't get into the details, but obviously DeepSeek was another example where maybe we can do these things at orders of magnitudes lower cost. It's reduced the cost of entry for a lot of enterprises. Another accelerator, getting companies to figure out how do I leverage this to be able to drive value. So industries everywhere, whether it's higher education, whether it's genomics research, travel agencies, NASA, auto manufacturers, media companies, everybody is trying to figure out how do we start using these technologies to take our data, our value, our differentiation, unlock that, and leverage AI in order to be able to innovate and drive new revenue opportunities for businesses. And we really do believe that VAST really is the only company that can truly unlock that value of that entire enterprise data corpus, with the key piece of that is being in real time, not just real time analytics like a fast response from a query, but being able to do it real time against real data as that data is being generated, as that data is being ingested, be able to immediately glean value from that without having to wait for ETL processes and batch processes that over time move those real-time data sets into an area where it could be analyzed. We want to be able to make it possible for you to analyze data at point of generation so I can get truly real-time insights. And that's what we're looking to solve with the Insight Engine. So how do we make that claim? Part of it is to understand a little bit how the enterprise pipeline differs from the training pipeline of the model builders. It looks similar, but there's some fundamental key differences. So again, it starts with data. It starts with all of the data. So this is the entire enterprise data corpus, right? This is G drives, this is OneDrives, this is email systems. These are file repositories and data lakes. These are object and blob stores. All of your data that might exist across many different locations. Being able to find that, index that, understand what you've got, that's sort of that first phase. The next phase is then preparing that. So which subset of that data do I want to unlock for a particular AI function or opportunity? So maybe I want to create a customer support chatbot. So I don't need all of my data, but I do want all of my knowledge base documentation. Maybe I want to have the chat history of every or the recordings of every single support call that I've ever had before. I want to have some of my core product documentation. All of that might be loaded into a system that I want to use to automate support through this chatbot. Or maybe if it's I want to create a content pipeline for marketing to be able to create content and collateral. So it might have your brand guidelines. It could have your core messaging. It could have some historical documents that you use for template purposes. Again, taking that enterprise corpus, funneling that down into what do I want to use for a particular AI opportunity. And then I'm going to go ahead and take the process of taking that raw data and I want to make that available for LLMs for these RAG opportunities by vectorizing it. So what that means is I'm taking the raw data, I'm chunking it into smaller subcomponents. So if it was a document, maybe I chunk it into words or phrases of that document. If it's a video, I'm chunking it into, it could be as small as a single frame, but it might be 10 or 15 seconds of a video that I want to chunk it into. Once I've chunked my video or my audio or my text into these sort of sub chunks that make up the whole, then I'm going to index those and then I'm going to vectorize those. So vectorization is the process of typically taking an embedding microservice like an NVIDIA NIM and then doing a mathematical, it's basically algebraic calculations against that chunk to turn it into a vector, to turn it into something that I can use as a comparison or a similarity approach from the LLMs, which we'll get to in just a second. All of those vectors and all of those indexes and all of those chunks of the core data all need to be saved someplace for querying with these large language models during the inferencing phase. And those are typically stored in vector databases. So I need to have some sort of a database, not just the source file, but also the chunks, indexes, and vectors of that file in a location for querying. Once I've got that, we move into the inference phase, which is the actual now chatbot that I use for support. So all of my chunks, indexes, and vectors of all of my support data is now in my database. I'm going to go ahead and use either a chatbot if I want to do it with a manual search, or maybe I've got an agent that's doing this. It starts by selecting the large language model that we want to use. Most enterprises will not make their own LLMs. They'll use a large language model from either an open source or a closed source vendor, but I'm going to take that LLM out of the catalog, and I may do my query against that model. If the model knows the answer, it'll reply back with an answer. If it does not know the answer, or at least not with high confidence, which will normally happen in one of these environments, that model will then go, okay, I'm going to go ahead and do a retrieval or a query of that vector database to get the results. So maybe I've got a question about how do I, troubleshoot a particular bug that I'm experiencing. So that model is then going to go and do the RAG operation. It's going to query the vector database. It's going to take the request that came in from the chat bot. It's going to vectorize that request. It's going to then do a similarity search against the vectors in the database, finding the answers and then the chunks of data that most likely are the correct response to that request. Those get ranked, which one is the most likely response, which then gets passed back to the language model, converting it into your native language and giving you the answer based on the data that was in your core enterprise data set. This operation is that retrieval augmented generation. It allows me to privately have my own set of data and be able to unlock the value of that through this vectorization approach. Now, of course, the results of all of this still need to be inferenced and logged for compliance and regulatory purposes, respective to the industry that you're in. And then subsets of those responses maybe get passed back in order to improve this going forward. That could either be by picking other data sets, or the responses themselves could become input into feeding the next set of vectors so that you actually can learn from previous responses and continue to tune that. And the rate in which we can take output becoming input and it now becomes part of that broader knowledge set, the faster we can continue to improve the quality of the output of these responses. So this is effectively the enterprise pipeline. The main difference is that middle piece, whereas instead of training a new model, you're vectorizing your enterprise data to make it available for those language models to do those querying operations against. I'm now going to double click a little bit into what's actually happening in the background. So this is actually more of a schematic approach of the previous slide. The previous one was more of a marketing slide. This gets more into the engineering of what's happening in the background. I'm going to make this much simpler for you to understand. So this really breaks down into a couple areas. These pieces here, that's the chatbot or the AI agent. This is where you actually do your queries and your questions and get your responses. Everything else is the data landscape where all those answers are being pulled from. So what's inside of that box? We've got 3 data storage layers here. We've got your sort of continuous data processing data lake in the upper left. That's for your unstructured data, files and objects, documents, texts, images, PDFs, videos. Those all get stored in the data lake. In the lower right, you've kind of got the data warehouse. So this is going to be more of just the structured data sitting inside of data warehouse services and tables. And then you've got your vector database or a graph database that could be used for the querying and similarity search of the data. So what's the process that happens? So when data hits the data lake, oftentimes what happens is a batch process kicks off that waits and says maybe every 15 minutes, 30 minutes, maybe the end of every day, you take all of this new data that's hit that data lake and you pass it through a set of embedding microservices. These could be provided through NVIDIA NIMs, but there's a variety of different microservices out there that exist that you could use to do these operations. What they do is they take that raw data that was in the data lake and does that process of chunking into, again, words or phrases, frames of a video, chunks of a window of a video, embeds each of those. So this is where it goes through the indexing and embedding, and then it saves all of that resulting knowledge embedding into the vector database. This group down below is then the retrieval microservices. All right, so the retrieval microservices now, when the request comes through, so for example, this user or an agent makes a question, what's the next 2-quarter pipeline for my North America sales region, maybe. The agent LLM probably doesn't have an answer to that question, and so it passes that request through a set of embedding microservices that embeds that prompt, what's the next 2-quarter pipeline for, embeds that into a set of vectors, that then does a semantic search against the vector database, which does a similarity. Is there anything in that vector database that knows the answer to the question of my next 2-quarter pipeline? If so, the response that gets passed down to a ranking microservices that then says what's the most likely correct answer, passes those most relevant results back to the large language model that then gives the answer to the requester. The next 2-quarter pipeline of potential closed business is currently XYZ. All right, so all of this data stores and microservices is the process of embedding, taking raw data and embedding it for search, and the process of actually performing that RAG search against a question that comes from an agent or a human. Now, there's weaknesses to the current system. What are the current challenges that most systems today have? First of all, this shifting from raw data to vectorized data is typically a very batchy process. Like I said before, at best it might be 15, 20 minutes. At worst, it could be daily. It could be more frequent or less frequent than that, but that's probably the right window. And what that means is that the data set that you're actually searching against is only as good as the last batch window. There's always going to be some level of lag between when data is created to when that data is available for search from many people trying to access that. The second limitation is in the vector databases themselves. So today's vector databases, typically in order to be able to perform, need to run inside of server memory. And in order to be able to scale those databases, it means more and more server, more and more memory space. And similar to the challenges of the data platforms under that Google model before, the more servers that get involved, the slower that vector database is going to run. And also it creates scalability limitations because there's only so many nodes I can spread it across. And also servers and memory cost a lot of money. So it gets very expensive and laggy the larger that vector database becomes. If all you're doing is a single chatbot, works great. But when you start rolling AI at scale from not just your customer support, but your marketing, your finance, your sales, your supply chain, your HR department, your engineering teams, your software developers, all of these use cases, when you've rolled AI out across your entire enterprise and all of your functions, now you're looking at not just vectorizing small amounts of data for a particular AI use case, but you get to the point where you're vectorizing your entire enterprise data set for a variety of different AI use cases over time. When you get to that point, these vector databases simply cannot scale to be able to support those environments. And so we need to solve that scale and performance problem. The third, and probably one of the most important, is security. Being able to have a security context of your unstructured data store, a security context of your data warehouse, a security context of your vectors, and be able to synchronize across those, because you don't want to have all of a sudden all of your data in your data lake that is very well secured with all of your different policies, have it all get vectorized and thrown into a vector database that does not have the same security context. You don't want to have an intern querying the financials that your CFO would have availability to. And so coordinating and synchronizing security policy across these disparate locations also becomes a significant challenge at scale that we look to solve. The final piece, of course, is complexity of integrating all this together. All these different moving parts from different vendors becomes a challenge. And we want to be able to make this very, very simple and turnkey in an appliance type experience. And that is fundamentally what the VAST Insight Engine is. So what is it that we will be showcasing? I'm talking to you about it today, but we'll be showcasing at NVIDIA GTC in just a couple of weeks, is a couple of things that we've added to our system. So the first thing is a semantic database. So we will be adding vectors to the VAST database. And so we now not just become sort of a table structure, but we can now do exabyte scale vector database that can get parallel access to that entire exabyte set. And so now you can all of a sudden eliminate that performance and capacity limitation of existing vector databases. We have moved, remember, our metadata, our write buffers, and all of our capacity down into persistent flash. So we can now get SSD performance, 99% of the speed as if it was local to the CPUs and GPUs, but at an exabyte scale data space. That's one key thing from a vector perspective. The next one is a scalable index. So again, indexes are not in memory of the servers, indexes are on our persistent disk layer. So I can now have infinitely scalable vector indexes that we can search against, giving us large capacities at, again, excellent performance. We will be able to leverage a container runtime inside of the VAST Data Platform to be able to run NVIDIA NIM microservices. So rather than needing to have external server clients in order to run your embedding operations and retrieval operations, those NIMs can now run natively inside the VAST Data Platform on our container runtime. Our data engine can automate these workflows. So that batchy process of as data flows in, and then at what point does that now get vectorized and chunked and ready for retrieval, we can now automate that process so that as data flows into the data store or the data into the data store, it can instantly trigger an event that vectorizes, that chunks, indexes, and vectorizes that and saves it into a vector database. And then finally, we get that real-time performance because we're also going to be supporting within the VAST Data software stack, we'll be able to support hosts that are running NVIDIA GPUs. All right, so again, a exascale parallel performing vector database, scalable indexes, microservices running natively within the platform, and automating the process of ingesting data, chunking, indexing, vectorizing, and then analyzing. So what is this now going to allow you to do? This is what it's going to look like in action. So you've got the VAST Data Platform. Today, you've got the database, the row and column table. You've got the data store, which is files, objects, and I need to add block to this. We've added the NIM catalog, so you'll be able to actually have the NVIDIA NIM catalog available to pull any of those microservices or any of those embedding services. We've added vectors to the database. And now as data flows into the system, real-time structured or real-time unstructured data, our data engine now says as soon as data hits the data store, that data engine will now instantly trigger an event. And that event would be the provisioning of an NIM microservice, taking that data, chunking it, vectoring, and indexing it, and then inserting those chunks, vectors, and indexes into the VAST database. That whole process from when a file is committed to the data store until it is chunk, indexed, and vectorized and available for search is only a matter of milliseconds. And so as data is flowing into the system, almost like a river, it's flowing through the data store into the vectorized database in real time. And so you can now do truly not just real-time inferencing, but real-time inferencing against a real-time data set at exabyte scale, at literally gigabyte, or petabytes per second of data ingest. Now, once it's been, the next phase here is security. So we use what we call atomic security. So atomic security in our environment says the same security context applies to your blocks, your files, your objects, and your tables, which includes your vectors. So any change at any of these locations is automatically inherited in any other one of these objects. So what does that mean? If I have a file that drops into my data store that has permissions by the finance department, only somebody who has security permissions in finance will have access to the resulting vectors from a inferencing search. And if at any point somebody changes their permissions, maybe they leave the finance department and move to another part of the company, or they leave the company, and those security policies are changed on the file object, it's instantaneously inherited by the vector. And so somebody who's doing a search one moment would get the response that they expect because they have permissions to that, maybe finance data or salary information. But as soon as you remove their permissions to the source file, the resulting LLM search would also lose permissions to the vectors and the chunks that are represented there. This is a huge, huge difference. In most operations, the tracking of that security between is a manual operation or is a very complex set of synchronizing these policies. It is inherent in our platform atomically. Change it once, inherit it everywhere. Final step, of course, is now that data is all ready for human and agentic AI operations. So again, this shows that process of data flowing into the system, flowing through, leveraging the NVIDIA NIMs for chunking, vectoring, embedding, and then securing that entire environment and allowing that to be available for these inferencing operations at scale. Not just for, obviously, one AI use case, but for tens or hundreds of thousands of AI use cases across the entire enterprise. So the goal here is to take all that complexity that we showed before and turn everything inside of that sort of shaded box into a single, effectively a RAG appliance that includes all of your source data, all of your vectorized and chunked data, and the microservices required to both do that operation as well as the microservices required to do the retrieval operations as part of a RAG pipeline within an enterprise environment. So what are we saying this is? It really is the world's first real-time, and we truly mean real-time, not just the inference itself, but the data. It's the first real-time retrieval engine, and also the world's first hyperscale vector database. We do have many very large customers that may want just this very large vector database to be able to support vectorized operations at exabyte scale, but maybe don't want the RAG portion of this. That is really up to either one. But both of these cases, these are very, very game-changing capabilities in the industry. And so that piece at the bottom, we see that the VAST InsightEngine with NVIDIA, it truly accelerates business insights by capturing your data, embedding your data, and retrieving that data through these real-time data flows. and making enterprise data instantly available and instantly usable for these AI-driven decision-making processes. We launched this in partnership with NVIDIA, or announced it in partnership with NVIDIA back in October. We've been closely working with their engineering teams to bring this out. It's currently in a state that we are sharing it with customers today. It's in beta with several customers that are using it. We're sharing it with customers that want to see it in action, but you will officially be seeing it more publicly in 2 to 3 weeks, 3 weeks, I believe it is, at NVIDIA GTC. We're really excited to have that event, and we'll have people in the booth that can answer any questions that people have, and how this can apply to your particular business. So how to get started today, if you want to learn more now, you can go to vastdata.com. We do have about probably the 30-minute announce video from earlier back in October that talks a little more depth about an InsightEngine. There's a bunch of different content that we've got up there around what we do for inferencing and for training. You can go to the Cosmos community. So this is a community that we also launched last year. Anybody who's interested in learning more about AI, whether it's the training, the inferencing, the whole thing, you can learn from other vendors, from other customers, we've got educational institutions, and just broader sort of thinkers in the AI space are participating here. So you can go to the community to ask your questions and get more information from each other or from us. And with that, I think we're actually very close to time. So let me stop the share here and take a look and see if we have time for maybe a question or two. There is a question: are GPUs shipping in VAST hardware? So first thing to answer that question, VAST doesn't actually ship hardware. VAST, the VAST data platform is really just a software stack. We do have hardware partners. So you think HPE and Lenovo and Supermicro and others that build hardware to our spec. But yes, we will be adding supported GPU server configurations to be able to support these operations when this is generally available. And I think we do have a couple other questions out there, but we are out of time. So what we're going to do is we'll follow up with any other questions that come through. If you do have any other questions, you can throw them down into the chat now, and we'll follow up directly with everybody immediately, or as soon as we can after this webcast. Hopefully this was helpful, gave you a little bit of insight into what VAST is doing and how we can help you be more successful in your AI adventures. Analia, I'll pass it back to you if you want to close it out.
Yeah, thank you so much, Aaron. Thank you, everyone, for joining. And again, just echoing what Aaron says, if you have questions, continue to throw those in the Q&A tab. Or, as always, email us at hello@vastdata, and we will put you in the right contact with the right person. So thank you again, everyone, and have a great rest of your day.